Good afternoon. We have come to the chapter of complex number and we will be doing the complex root theorem. Today I'm going to prove to you this theorem. Now the complex root theorem states that if a plus bi is a root of the polynomial p of x of degree n greater than 2 with real coefficients, then a minus bi is also a root of the polynomial. There are a lot of words here. Now let me just simplify for you. Now polynomial of degree n greater than 2 means what? Means p of x can be expressed as a x to the power of n plus b x to the power n minus 1 plus c to the power n x to the power n minus 2 dot 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 dot, such that n is greater than or equals to 2. Now a, b, c, so the coefficients must be real, all right, real numbers. So maybe a, b, c dot 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 is a set of real numbers. Now if a plus bi is a root, that means if you substitute, if you replace x with a plus bi, then you will find that p of x will be equals to 0. So pe into, pa plus bi will be equals to 0. It implies also p a minus bi equals to 0. Now it states that if it satisfies all this, then p, you place x with a minus bi, and this expression will be equals to 0 as well. Now let me show you what is the importance of why n must be greater than or equals to 2. Now if n equals to 0, then you will find that p of x is equals to a, because a polynomial cannot have negative coefficient. So you will have p of x equals to a. Then it has no roots if a is not 0. But if it's 0, then it has infinite roots. So this thing doesn't hold if n equals to 0. Now what happens if n is equals to 1? If n is equals to 1, then your p of x will be equals to ax. Now then, you'll find that it will only have one root where x is equals to 0. Then this thing doesn't hold as well. Now let's do the case when n equals to 2. Now if n is greater than or equals to 2, what will happen? Your p of x, as what we have shown you earlier, can be written as this. Then p a plus bi must be equals to 0. Now let z be equals to a plus bi. Alright, implies p of z equals to 0. Okay, let's replace x with a plus bi, or let's replace x with z. Alright, now then you have a z to the power n plus b z to the power n minus 1 plus c z to the power n minus 2, so on and so forth, it must be equals to 0. Now if you take the conjugate of for the right and left, alright, see what will we get? Okay, I take the conjugate of this and this. Now the conjugate of this, of the sum, will be the conjugate of the individual complex number. So it will be conjugate of this plus the conjugate of this plus the conjugate of this must be equals to 0. Now this, what will you get? You will get A conjugate z to the power n plus b, because conjugate of a real number is itself. Z n minus 2, this bar here, equals to 0. Now what does that mean? It implies that if you compare this against this one, you realize that I replace z with z bar, alright, and that is equals to 0. So implies that p of z bar is 0. Implies that a minus bi is a root of px. Okay? Now, we have come to the end of the proof. Now, this, are you aware that this part to this part, are you aware of this identity? Now, let me just show it to you that p of z, let's say I prove this to you. Now this is not part of it, we already come to the end of the proof. Now I'm trying to prove this part, okay? Just in case some of you do not know. P be a plus bi and q be c plus di. So I add the two complex number up. P plus q will be equals to a plus c, the real part plus the real part, then the imaginary part plus the imaginary part. Now if I conjugate both sides, if I take the conjugate of both sides, alright, now conjugate of this will be a plus c minus b plus di. So what will I get? I will get a plus c minus bi minus di. Now this is a minus bi. A minus bi is conjugate of p. C minus di is conjugate of q. So you conjugate the sum is equals to the sum of the conjugate. Okay? Now for that we have come to the end of this proof. Thank you for watching and please subscribe to our video. Thank you.